Okay, Reynolds average Navier-Stokes is most or commonly used turbulent models in the industry because of its simplicity and its low computational effort compared to the other turbulent models. We discussed in the previous part that Reynolds average Navier-Stokes has certain limitations, such as its accuracy to capture the detailed fluctuating flow, but again it is quite useful in the daily application because of its low computational effort, but still capture such important features like drag force maybe the lift force, or maybe if you want just to compare the temperature distribution over time, or maybe like not a detailed fluctuating flow, it will be not an issue. And the basic idea of the Reynolds average Navier-Stokes is by constructing this kind of governing equation by addition of this the Reynolds stress, because sometimes the problem with the averaging is the fluctuative term itself, and the fluctuating term here separated here with the prime means that or it also known as the Reynolds stress. So by averaging this, we can model or calculate the value of the Reynolds stress by introducing some new values, such as the turbulent kinetic energy, which is defined by this equation, and then we also introducing another term like the turbulent dissipation rate and specific dissipation rate, and each term or the turbulent kinetic energy, also called kappa, if solved with the equation of turbulent specific dissipation rate, or epsilon, called the kappa epsilon turbulent model, or let's say if we use like the turbulent dissipation rate, it will create the kappa omega model. So everything is just about equation basically, but in this part I would like to discuss the practicality of their like how to use this turbulent model, or what is the benefit and its drawbacks. And again, the idea of the RAS model is to calculate this Reynolds stress by using or by introducing some new parameters, which is actually not you cannot find it here in the nature, like the turbulent kinetic energy or this specific dissipation rate is actually just like average value, which you cannot measure actually in the like a physical flow. Okay. And we are also introducing the turbulent viscosity, which is not a real viscosity, but like like something that behaves like a viscosity in the turbulent flow. And this is the first model, which is the Spalart-Almaraz, which is the simplest model because we only use one equation. Let's say if we want to use like a kappa, omega, epsilon, we will use more than one equations. So Spalart-Almaraz only utilize one equation, which is very simple. And we find here the nu, and the bar, like wavy bar on top of the nu is called tilde. So sometimes in OpenFOAM we find the nu tilde, it means this term. And because of its simplicity, this is considered as the simplest RAS model. No, maybe the simplest that used in the industry, I mean. And this is very doesn't need high computational effort because it is only one equation, and it is very useful to use in the aerodynamics applications. Let's say if you want to calculate some lift and drag of a body, using the Spallard-Almaraz will be sufficient. But if you want to get more detail about the wake flow over airfoil or aircraft, let's say, or if you want to predict the stalled condition, sometimes it is not works that well. But again, there's no such a perfect turbulent model, and there is always a trade-off. Okay, this is Spallard-Almaraz, and then now also commonly used also for the turbo machineries like pumps or maybe the centrifugal compressor. Use this model of Spallard-Almaraz. Then the first turbulent model, or maybe the well-known turbulent model, is the kappa epsilon model, which consists of two equations, which are the kappa and also the epsilon, as its name suggests, of course. And it is called standard because like it has more than one reference to this model, or one, like more than one works that referring to use this kind of equation. So this model or this equation is called the standard K epsilon model. Basically, it is not intended or not historically it is not designed for the specific kind of applications, but in practicality this model is have more benefit for the high Reynolds number flow. For example, if we have like a free stream in the near of the building, in the interaction of the flow across, like for the building, and the free stream, let's say, if you want to simulate the wake region or far away from the body, the K epsilon model is have a beneficial for this. But because of it is like a high Reynolds number model, so sometimes it's not quite accurate to predict the nearby value or nearby the wall values, and maybe it is not also like stable for predicting the near wall values. This is the K epsilon in general. Then we also have a kappa omega. Here we solve the kappa and the omega value. And kappa omega is basically the opposite of the kappa epsilon. This is like the low turbulent model, or Reynolds number turbulent model, which is beneficial to be used in the low Reynolds number, like nearby the wall. And it is also beneficial for the adverse pressure gradient. Let's say we want to like simulate the diverts, like a diffuser, or like separating flow or high spreading jet, let's say. The kappa omega model is better than the kappa epsilon, but this model is like sensitive to the inlet condition. So if, let's say, we are like simulating a high domain flow with object in the middle of the domain, and we input the free stream condition, sometimes the inlet, if we are not inputting the right initial condition or initial values, will be problematic to the convergence of this turbulent model itself. So sometimes it is very unstable. Then this is maybe the like some people said that it's like the queen of the turbulent models, because it is the kappa omega SST, or shear stress transport, is combining the benefit of kappa epsilon and kappa omega. So this term 1 minus f1 is basically known as the blending function, which if we set the blending function as 1, it means that 1 minus 1, it will diminish this term, which makes this equation or this value become fully kappa omega. So here it means that if it is 0, it will be like kappa omega. And if f equals to 0, so the value will be kappa epsilon here. So we can expect that, or we can understand that the value of the blending function is the function of the wall distance. So nearby the wall, the f1 become close to 1, means that everywhere here will be solved by the kappa omega model, and far away from the wall the f1 is approaching to 0, means that this region will be fully resolved using kappa epsilon. So this model is basically combining the beneficial of the kappa omega and kappa epsilon in one turbulent model. That's why this kappa omega now become very popular and maybe mostly used if we don't have any initial guess of when to use the kappa omega or kappa epsilon or any other models like kappa epsilon RNG, let's say, and any other things. But again, this all this all model, or maybe this all explanation is just all about the educated guess, and we must again validate our result and then see the detailed flow. Let's say if we want to simulate the flow over our file, sometimes it will be different if we want to calculate the lift and drag, or if we want to calculate the shear stress, let's say, or maybe if we want to focus on some specific case or the wake region or the length of the vortex, let's say, it will be completely different for each turbulent model. So again, there's no general rule which is the best turbulent model, but you can use this explanation as the initial educated guess for you. And this is some again a rule of thumb or educated guess to estimate the values of the turbulent parameters. Let's say if we are using OpenFOAM, let's check our file. Let's say let's check our previous model here, maybe this one. It is always some turbulent parameters here like the kappa, epsilon, and omega, and the values here you must always calculate or estimate by using some specific values which you can use here. You can take a screenshot if you want. And for internal flow, we estimate the epsilon by using this equation. It is easily used. The U reference is the inlet velocity, and the L is the sometimes use the diameter times 0.038, and that's all. It's easy. And the external flow is basically the same, but we have the beta factor here that you can use this table to estimate. And once again, I have to emphasize that these all are just estimating value. You can tweak a little bit your values, and it will not change the result, because along with the calculating process, these values will be diminish over the number of iteration. But it is very crucial to maintain your stability, especially in the starting of your iteration. And this is also the mu t, nut is actually like nu t, so it is like a nu with t or turbulent viscosity. And one feature that every turbulent models have is the wall function. So wall function is basically resolving the value or resolving the velocity distribution in the y direction is the velocity, or u plus, it is not actually velocity, it is like a non-dimensionalized velocity, and the x axis is the y plus, or like non-dimensional height far away from the wall. The actual function or actual curve is shown in this black curve. So if we actually solve this flow, like using Navier-Stokes equation or using direct numerical scale simulation, it will be shown like this. But you know that if we want to solve this boundary layer, it will be need a very thin mesh. Let's say if we have a very high Reynolds number, sometimes the mesh is just like in the couple of millimeter for a huge aircraft, let's say like a couple of meter, and that will be not feasible. And the using of this wall function is actually or basically making this curve, like if we don't have like the right amount of right thickness of the wall like this, if we use this mesh, is not, if it's the mesh not that smooth, the curve of course will be like a break somewhere here, so the calculation of the velocity distribution will not as realistic as this. By using wall function, we can actually make this curve without really need the mesh here and here. It is very beneficial if we want to solve like a simple like a simple problem with like an aircraft. If you want just to solve the drag, lift and everything like that, it will be beneficial. But if you are dealing with secondary flow nearby the wall, like like a very intense mixing three-dimensional vortex nearby the wall function will not works that well, so you must fully resolve the mesh, and again that will need a high computational effort. And if we use piecewise linear, it means that it is just basically follow the linear interpolation of this mesh. And these are the turbulent models in the RAS family that provided in the OpenFOAM. You can explore it one by one, but the general rule is just the same, which is the K epsilon for high Reynolds number, K omega is for the low Reynolds number, and the K omega SST is the combination between K omega and K epsilon. The other terms you can explore it one by one, but if you are not in a very specific works, it will not be rarely used by you. But if you are lucky, you will find a journal or maybe a reference that previously used the specific turbulent model that will be beneficial for you to follow that journal or reference.